In this lesson, we're going to talk a little bit about an annuity. It's something that actually makes a lot of sense and you probably understand intuitively, even if you've never heard the word before. So let's just start off with an example talking about why this is important. Um, in our last lesson, we talked about compound interest and we saw that we can build money that if we make an investment or if we borrow, and it's just going to keep building an amount over time through regular interest. So if we invested just once, $67,000 at an interest rate of 7% per year compounded annually, that's not an unreasonable investment amount. We'd have $1 million 40 years later. So all you need to do if you want to retire a millionaire is not work the rest of your life. Just invest $67,000 now. And then when you retire, if you never work, I guess you don't have to worry about that. But in retirement time, you'll be able to just have $1 million. So the only problem with that is that you probably don't have $67,000 sitting in your bank account right now because you're a teenager. So just saving $67,000 one time, probably not something realistically you can do. So an annuity is the idea that instead of just taking one chunk of money and investing it, or borrowing it for that matter, which is unrealistic in most situations, what we want to do is we want to make regular investments on a regular interval. So maybe you don't have $67,000 to put in a bank account right now, but maybe you can put in $20 a week or $50 a week or some other amount. Um, and then eventually you'll have all these little chunks of savings all gaining interest, all adding together, and at the end you'll have quite a big sum of money actually. Same thing is true with payments. No one goes and buys a car or a house now, and then in 30 years just says, okay, how much do I owe you? And I'm going to pay you back in one shot. If you buy a house that you pay back regularly, usually either biweekly, twice every other week, or monthly. So either way, you make regular payments on a regular interval. That's what an annuity is. It's when you make regular payments on either an investment or a borrowed money so that you kind of either build up or pay down something with multiple payments instead of trying to do it in one big chunk. So these are super common. They're used all over the place. Mortgages, in most investments, a lot of people end up setting up kind of an automatic deposit into an investment on their paychecks. So for instance, I put $250 a week, or sorry, $250 biweekly into an investment, and it just does that automatically. It automatically deposits every paycheck I get. So that's the idea behind annuities. Now, there are two types of annuities. It's a very subtle difference. Um, these pictures will hopefully kind of try to explain it to you. So an ordinary annuity is when you make an investment starting at the end of each period that you're going to invest at. So if you decide, okay, you know what, my New Year's resolution this year is to invest $1,000 every year for however long I want to do. In this case, this example, we're going to do it for 5 years. And so it's like, oh, I don't have $1,000 right now, but at the end of this year, I'm going to invest $1,000. At the end of the next year, I'll invest $1,000 and so on. So that's what a regular annuity looks like. We decide to start the investment or the borrowing. We don't start paying immediately. We start paying at the end of each compounding period. An annuity due is the same idea, except that instead of investing at the end of each period, we're going to invest at the beginning of each period. So I decide, okay, New Year's resolution, I'm going to invest $1,000 every year. I've got $1,000. I'm putting it in now, and I'm going to do that at the beginning of each year for the next several years. As far as the mechanics of these goes, the math is pretty similar. There's one little difference in the equations, but we're going to just have a list of equations to use, and then we're going to pick the right one based on the scenario in the question that we're given. So just be aware that regardless if you remember the names or not, there's one equation for putting money in at the end of each period and one for putting in at the beginning of each period. All right, so in our example here, we're going to save $1,000 at the end of each year. So this is the ordinary annuity because we're putting it at the end. So we're going to set aside $1,000 at the end of each year for the next 5 years so that we can take on a vacation 5 years from now. How much are we going to have for our trip at the end of this 5 years? We'll put it in at 5% a year compounded annually just to make the math relatively simple. just so you can see how this works. So here's what we can do. If I actually just scroll up just a little wee bit, if I take this money here, so I'm going to put this $1,000 in right there at the end of the first year. And what you might notice is that that investment is going to build interest for 4 years. So it's basically taking us from the beginning of year one to the beginning of year four, but that's a 4-year gap, not a 5-year gap. So what that means is that my first investment, if we remember our compound interest equation, essentially how much we're going to have at the end of the 5-year period is going to equal the amount that we put in at the beginning times 1 plus I, in this case 1 plus 5% is 1.05, and that's going to gain interest for 4 years. Now similarly, I can also invest, or I will also invest, this $1,000 for 3 years. So I'm going to also add in $1,000 at 1.05 for a 3-year investment. And then I'm going to do the same thing for the next $1,000, which will be for 2 years, the next $1,000, which will only be for 1 year, and the final $1,000 will not get any interest on it at all. I'm literally putting it in at the end of the 5th year and then saying how much money do I have right now. So the pattern is going to continue as 1,000 1.05 squared, 1,000 1.05 to the 1, and 1,000 times nothing because it's not going to get interest at all. Now, if I plug these all in, this one I can do pretty easily. That's 1,000. 1,000 times 1.05 is 1,050. And then in my calculator, what I'm really going to do is just keep multiplying by 1.05 one at a time, because that's going to keep giving me my higher powers. But however you do it, this one's going to be 1102.50. This one will be 1157.63. And this one will be 1215.51. Okay, so those may be a penny or so off because of rounding error, but approximately those are correct. And if I add up all 5 of those, which is going to be basically my total investment, I'm going to have $5,525.64. Okay, so that didn't seem too hard. This is just regular compound interest. However, I had to do 5 equations. And even though they're simple, they weren't that hard to do, I still had to do 5 of them, and no one likes having to do multiple equations. Now, forget doing $1,000 every year. Pretend for a second that you put in maybe $50 every week. Well, that means that over 5 years, you'd have to do 52 times 5. That's 260 investments. So you'd have to do something like this, but 260 times instead of 5. That seems like a real pain. So we don't want to have to do it that way. Luckily for us, somebody smarter than us came up with an equation that works out just fine. And the equation looks a little bit like that. It's future value equals, now here's one of our new variables here. PMT is a payment amount. So in this case, we're putting in payments of $1,000. It's whatever that regular payment is. Again, whether it's an investment or borrowing doesn't really matter. So in this case, that's $1,000. And then 1 plus I is exactly what we expect it to be. The I is the same as it always has been in the compound interest equations. N is the number of compounds total, which in our case is also the number of payments total. So what we'll do here is we'll plug in what we know. This one I think is simple enough. I'm not going to make a list down the side of what things are. We're going to put $1,000 in. And despite that this doesn't look like a pretty equation, it's actually not that hard to do. So 1.05 to the exponent, what did we say? Oh yeah, 5 payments, only 5 payments, minus 1 divided by 0.05, which is our I without the plus 1 in front of it. Okay, and I'm just going to do this in maybe a couple of extra, well, I'll walk you through the steps on your calculator. So make sure that you do BEDMAS correctly on this one. Actually, I don't need a big bracket anymore. 1.05 to the exponent 5, you'll plug that in, get a number. Subtract 1 from that, hit equals, get a number. Divide by 0.05, get a number. And that bracket as a whole is going to be 5.52563,125. Again, keeping more decimals than I need. And when I multiply that by 1,000 and round off to the closest cent, I get $5,525.63. Okay, that is not a pretty equation, but I only had to do one of them. And it turns out that this one's irrelevant of how much my payments are and how often I make them. So I could make 1,000,000 payments this way. It's going to change my I and my N, but it's not going to make the equation any longer. Whereas when we go up here, doing 1,000,000 payments is going to mean that I have to do 1,000,000 lines of math. Don't want to do that. Okay, if we take a look at this, we got 5,525.64. Down here, we got 5,525.63. We're 1 cent off. This one actually is the correct one. This one up here, I think there was a little bit of rounding up we did on a couple of these that both gave an additional penny, and it should have only really happened once. So either way, if we're off by 1 penny when we're talking about $5,500, I don't think we're too worried about it. So this is the equation, well, this is one of the equations that we can use to solve our problems. There are actually 4 equations, and I realize no one wants to have to memorize 4, so don't memorize 4. Look them up when you need them. Basically, all you have to do is ask yourself 2 things. One of them is, do I need to know the amount that I will have in the future? So do I need to figure out how much I'll have later down the road? Or do I need to figure out how much I have now based on what my things will be? So yeah, do you want to know the amount you'll have later, or do you want to know the amount that it's worth now? And then is it going to be payments at the end of each period for an ordinary annuity, or is it going to be payments at the beginning of each period for an annuity due? And the only difference between them is this one little extra factor at the end, the 1 plus I. And really what that's doing is giving one more compound period of interest to every payment. So again, don't worry too much about where these come from or why they work. Just realize that they do, and basically plug them in. All right. So now that we've done that, let's take a look at this one. Actually, I'm going to leave those on the screen so we can see them. Emily recently started a part-time job. She is saving for a car, which she will need when she attends college 2 years from now. She plans to deposit $200 at the end of each month into an account that pays 4.8% per year, compounded monthly. How much will Emily have saved at the end of 2 years? All right. So first of all, let's decide which equation it is that we need to use. She is going to put in the money at the end of each month. End of each month means that we're going to use an ordinary annuity. And we want to know how much she'll have at the end of 2 years. And because of that, we want to use this equation here. So end of each period, and we want to know how much she'll have in the future. So that's all it comes down to, is you choose which equation you need to use based on whether it's payments at the end or payments at the beginning, and whether it's you need to know the amount later or the amount now. All right, so from that equation, let's actually do our little thing at the side here. Our future value is what we want to know. Our regular payment, we're told that she puts in $200 per month. Our interest rate is 4.8%. That's per year. But we have to divide by the number of times we're going to compound in a year, which is monthly, or 12. And 4.8% divided by 12 gives us 0.004. Don't forget the 4.8% becomes 0.048 once we divide by 100, and then divide that by 12 as well. And similarly, our N, our number of compound periods, which in this case is also our number of payments, is going to be every month for 2 years. So 2 years times 12 gives us 24 payments. Okay, so we use the equation future value equals payment 1 plus I to the n minus 1 over I, and then we're good to go. Okay, so future value is equal to 200, 1.004 to the exponent 24 minus 1 over 0.004. All right, when we do that bracket, again, play with BEDMAS, make sure that you're doing it correctly. Different calculators work differently, but you do the base to the exponent, 1.004 to the exponent 24. I'd recommend hitting equals then, getting a number. Subtract 1 from that, hit equals and get a number, and then divide by 0.004, hit equals and get a number. And when you do that, that entire bracket ends up being 25.137075. And when you multiply those together, your total future value will be $5,027.42. Okay, so we probably could have done the same by investing, I don't know, $4,500 now or something like that. However, again, most people don't just have a large amount of money for investing at any given moment. If you did, you probably don't need to invest. So we can't make one big chunk, or Emily can't make one big chunk investment to get it, but she can make $200 a month. All right. Now, unfortunately, we have to keep referring back to these equations, even though they're not really handy for us to look at, but that's okay. I will put them on the screen when we need them. This question here is actually a completely true and realistic question. This is exactly what I did. Unfortunately, I waited until my 40th birthday to do so. But on my 40th birthday, I decided I'm going to start investing $250 biweekly, so every paycheck I get, into a savings account that pays 5.2%. Okay, maybe the 5.2% interest is a little bit of a dream. I don't quite make 5.2% interest. I make some, but not quite 5.2. So 5.2% per interest per year compounded biweekly. So we're compounding the same as our payments. And I plan on retiring when I am 55.5 years old, almost to the day, actually. It just happens to be my retirement date. How much will I have saved up at this point? Okay, so this is an annuity because I'm making regular payments. Now, if I read the question carefully, I started investing $250 biweekly on my 40th birthday. That means I'm making payments at the beginning of my time. So I have to use an annuity due equation, paying at the beginning, not paying at the end. And I'm doing it until I'm 55.5, which means that it's really a total of 15.5 years because I started doing it when I was 40. Okay, so our future value is what we're trying to find. Our payment amount is $250. Our interest rate, I, is 5.2% divided by 26, since we're doing this biweekly, and 5.2% divided by, where is it, 26, is 0.002. Our number of payments, I'm doing this biweekly, so 26 times a year for 15.5 years. Oops, 26. 15.5 times 26 means I'm going to make 403 payments. Okay, so 403 payments. So now we set it up, and as I said, this was an annuity due because we're paying at the beginning, and it's a future value that we want. So the equation, if you look at your sheet or scroll up a little bit or go back in the video, whichever is convenient for you, future value equals the payment amount times 1 plus I to the exponent n minus 1 divided by I. And now we add on that little extra term because we're making our payments at the beginning instead of the end, so we'll build a little more interest. So we add on the 1 point I. Okay, plugging in the values that we know, 250, this is going to be 1.002 to the 403. minus 1 divided by 0.002, and this is going to be 1.002. Okay, I'm going to just do this bracket by bracket so we try not to make too many errors. That the square bracket, we do 1.002 to the exponent 403 and hit equals, subtract 1, hit equals, divide by 0.002, hit equals, and that should be 618.5664303 or something like that. I kept a lot of decimals there, probably don't need to. And then we still have that little 1.002 at the end. All right. And when I multiply those three numbers together, I get out $854,950.89. Okay, it's not the $1 million retirement plan I was looking for, but I also started a little bit later than I probably should have, waiting till I was 40. If I'd started this at age 20, I'd probably retire a very, very rich person. But you know what? We all learn a little late in life, unfortunately. So $154,950.89. Now, for part B, I just want to see how much I would have had if instead of investing it at 5.2% a year, because it's not really that much. 5.2% is kind of low. Maybe if I just shoved this money into my mattress or whatever and saved it that way without any interest whatsoever, I'd have just about as much. So what I'm going to do is take how much I invested per, or how much each payment was, and instead of giving it any kind of fancy equation, I'm just going to say I made 403 savings of $250. And that would give me a total of $100,750 in savings. So yeah, sticking it under my mattress to get me 100,000, putting it into an account with a little bit of interest on it, 5.2%, again, pretty reasonable, is going to get me 154,000. So 1.5 times as much just by investing. And by the way, I know it's not realistic to do either of these two things, but what is putting it into an actual real investment instead of just throwing it into a savings account, which will easily get you should easily get you 5.2% interest a year. And the equivalent, the no interest, is essentially leaving it in your checking account or your cheap bank account, which pays you such a small amount of interest that it becomes insignificant. So if you can transfer some of that money into an investment that actually does pay a little extra, you can see that you're going to get a fair bit more money. All right. Now let's take a look at Katrina in example 4. And Katrina is going to purchase her first car. Yay, Katrina. Okay, her bank gives her a car loan with payments of $229 per month starting today for 6 years at 10.5% interest per year, compounded monthly. So that's how much it would make if she made regular payments until the car was paid off 6 years from now. I want to know what the car is worth today. So if she just paid cash today, how much would it cost her? So there's no interest built up whatsoever. It just paid off all at once. Okay, so let's put in the numbers that we have and the numbers we want, and then we'll see which equation we need to use. We know that the payment amount is $220 or $229. We want to know what the present value is because we don't know that. So question mark. We know that the interest is 10.5% a year divided by 12 since it's per month in this case. And that's going to give us 0.00875. Not pretty, but at least it's actually exact. There's no more decimal places to keep track of. And the number of payments that she would have to make is $229. Sorry, what am I saying? $229. 12 payments a year for 6 years, which is 72 payments. Okay, so the next thing we need to do is figure out exactly which equation we want to use. Now, it talks about her making her payments starting today, so paying at the beginning. And it also mentions that we're trying to find a present value. So I look through my four equations, and you know what, for this one, what the heck, I'll scroll up for a second. We have this one finds our present value if we pay at the end of each period. This one is our present value if we pay at the beginning. So this right here is the equation we want to use for our calculation. So I'm going to go down here and copy that equation into this spot. All right, so present value, oops, let's actually make that work. Present value equals payment amount times, this one's a little bit different than the others we've been using so far. It's got a 1 minus 1 plus I to the negative n over I and 1 plus I there. Okay, so now in this case, we know that the payment value is 229. This bracket is going to be 1 minus 1.00875 to the exponent negative 72. Don't get too caught up on the negative exponent. You just plug in a negative number in your calculator. It works out just fine. And that should be over 0.00875. And then this bracket is just 1.00875. Okay. Now let's make sure we got this middle part right. So what I would do in this, and I'm going to use one more step in this one just to make sure we're not too lost or confused. I'm going to do the 1.00875 to the exponent negative 72. Now check on your calculator if it's giving you some kind of weird error. You might be hitting a minus sign instead of the negative sign, which in any situation other than your calculator shouldn't make any difference. But sometimes calculators have a negative button, which is different from the minus button. So you may have to look for it. Either way, when you plug in 1.00875 to the exponent negative 72, what you should get is a value less than 1. It's kind of like going back in time. So you would expect a number less than 1 on this. In fact, it will definitely have to be less than 1. And the number you should get if you're doing it correctly is 0.53405325 Again, probably don't need to keep that much accuracy, but I will in this case just to see that we're doing it right. Okay. And I'm going to point out that if you get a negative answer for your present value, it's usually because people aren't actually plugging in 1 minus 0.534. It's because they're doing 0.534 and then hitting minus 1, which is not the same thing. Order of subtraction does matter. Okay, so when you do that, clear your calculator, plug in the middle bracket, the 1 minus 0.534, blah, 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 divide by 0.00875, and you should get the number 53.25105,699. Again, maybe a little different if you round it off, but not a big deal. And then we still have that 1.00875 at the end. Multiply all three of those numbers together, and you get out $12,301.19. So essentially what that's saying is that Katrina's car, if she just went in today and said, I want to buy that, I have cash in my pocket, can I take it? The price would be $12,301.19. Or she can choose to make payments because, again, a lot of people, when you're younger, you're not going to walk into a place and have enough to buy a car out of the money in your pocket. So usually we will have to make payments. And just to make a comparison here, if she did end up actually paying the payments, the $229 per month for 6 years, how much would she pay for it that way? So in this case, it's just a matter of saying, well, she paid $229 a month times 72 months. And when you multiply those together, you get out $16,488. So she ends up paying significantly more for the car, a little bit more than $4,000 more. So about a 1 1/3 what it would normally cost, but that's the cost of borrowing money for a while. So if you don't have the money to pay for it up front, you're kind of borrowing that money and paying it back slowly. You're going to have to pay it back with some interest. All right. One more. Let's see how this one goes. Um, so Taylor recently graduated from college and owes $25,000 on a student loan. Payments must be made at the end of each month for the next 5 years. Interest is calculated at 6% per year, compounded monthly. So let's figure out how much the payments are going to be. Okay, so we're trying to figure out how much the payments are. I'll put a question mark beside payment. We know that the current value that Taylor owes is 25,000. And the interest rate is 6% a year, compounded monthly. So 6% divided by 12 is 0.005. And the number of payments that she's going to have to make is 5 years at 12 payments a year, or a grand total of 60 payments. Okay, so again, looking back up to our possible equations that we could use, Taylor is making the payments at the end of each month, so it's an ordinary annuity, and we have a present value known in our equation, so we have to use the present value ordinary annuity question or equation, and I'm going to copy that down here. So present value equals the payment amount 1 minus 1 plus I to the exponent negative n over I. And then we start plugging in the things we know. So I know that the present value is $25,000. I don't know the payment amount. That's what I'm going to have to solve for. And inside that bracket, I get 1 minus 1.005 to the exponent negative 60 over 0.005. Okay. Now in that bracket, actually, sorry, I'm going to do this one as a square again, just to make sure we don't do any crazy mess ups. 1.005 to the exponent negative 60 is 0.7413729196. And that makes that overall bracket, if I punch everything in correctly, which I hope I do, 51.72556.075. Again, possibly with a little rounding error. And then to find the payment amount, I'm going to divide both sides by that number. And when all is said and done, my payment amount should end up being $483.32 per month. Okay, so that means that for her student loans for the next 5 years, Taylor will owe $483.32 per month. And for part B, we're just asked to calculate the total amount that she repaid on her loan, which again is just to compare how much basically interest she paid in total. And we know that she made payments of $483.32, and she made 60 of those. So if we multiply that by 60, we get $28,999.20, which is about as close to $29,000 as you can get. So essentially, she borrowed $25,000 for her education, and she has to pay back $29,000 for her education. So $4,000 of interest. Again, when you consider what you're getting out of it, probably not a bad deal. All right. Now, one thing that I've glanced over, and I'm just going to point out now, I didn't feel a need to point it out earlier, is that when we're doing annuities, it turns out that this equation only works if the compound period of the investment is the exact same as our regular payments. So if we want to make a payment every month, then this will only work if it's compounded monthly. If we're doing it biweekly, it'll only work if we're compounding biweekly. And if we're doing it annually, it only works if we compound annually. Now, there is a conversion equation you can use to change your I value if you compound, let's say, for instance, compound monthly, but invest biweekly. But honestly, doing that's a little bit beyond the scope of the course. So all the questions that I'll tend to give are ones where the um, interest rate, or sorry, the compound periods are the same as the investment periods. And honestly, even if they aren't, it's usually just we pretend it's compounded at the same rate. So even if it is compounded monthly and we pretend it's compounded biweekly, the answers will be off, but they won't be off by a horrific amount. So if you're just trying to get a ballpark idea, then it'll work out just fine either way. Anyway, I think that's probably all you need to know for annuities right now. Again, not pretty equations, but they're really not that hard to solve as long as you plug things in the right order and follow BEDMAS. So I'll leave you at that. You've got some questions you can try and refer back here if you need to.